Thank you, Kim and the team. I really appreciate the opportunity to present on Science Week, and I'll be talking about weather and climate information. So there's an absolute data explosion going on, which is fundamentally changing the way operational meteorology is being undertaken. This is both with weather and climate models and through observations. There's an explosion means that we're running models at finer and finer scales. So we have global weather models at 10-kilometre resolution and finer scales down to a kilometre or less on regional models. Our seasonal prediction systems are down around 50 kilometres, and climate models are currently being operated, global climate models, at 50 to 150 kilometres. And there's reanalyses to match this. So you can imagine the data volumes are extraordinarily large, with multiple petabytes for some of these data sets. And then there's other climatologies for lightning, fire danger, and so forth. To further increase this, there's generally a move to having multiple versions of model runs and forecasts. So the models are run repeatedly with slightly different initial conditions, and that's to explore the range of uncertainty and potential scenarios that are feasible. And this is not happening just in the weather forecasts, but for example, in the Bureau of Meteorology, they're forecasting ocean forecasts, waves, tsunami, hydrological forecasting and smoke models, and things like fire behaviour imminent. In the observational space, we have 10-minute updated high-resolution satellite data. There's new radar capability with 5-minute updates. An extraordinarily amount of information that's available. This is a huge opportunity to leverage this in support of decision making and to build resilience and adaptation. Just to give you a couple of examples, and I'll just of just this kind of fine detail. I'm sure you'd agree with me when you look at this satellite picture or the radar or these model runs. There's just an extraordinary level of detail, and that'll be part of the challenges, is actually dealing with this vast amount of information and getting the right tools to support decision making, and I'll touch on that towards the end. But first I want to talk a little bit about particularly the models. So you really need to understand what you're looking at, because things are never perfect. A model is by definition wrong, but models are useful. First step for models should be verification. So for weather forecast models, we verify against what's happened. There's a little example there at the top which shows the amazing improvement in forecasts and maximum temperatures, where the 7-day forecast is now as good as the 3-day forecasts were less than 20 years ago. Seasonal models are compared against hindcasts, effectively what's happened in the last 30-odd years. And climate models generally run to look at what's happened over the past 100 years. And you ask questions such as, do they replicate the long-term trends? Are the spatial patterns realistic? Do they replicate key processes such as El Nino? And again, with reanalysis, also a key asset for supporting analysis over a whole range of activities. You can use site observations. So let's dig into some of the gotchas. First of all, to understand your data, one example is resolution. And what does that mean? It means, I've talked about the size of our grids getting down to hundreds of meters, but the smallest features you can actually resolve the order of 3 to 4 times that grid size. And that means things like coastlines and topography are smoothed. To give you an example of just how smooth, this is a cross-section of the topography across the Great Divide. We've chosen to look a line through Mount Kosciuszko to highlight the challenges. So there's a digital elevation model in black, and what a global climate model thinks that terrain looks like. So clearly it's, there's missing a huge amount of detail. There's not the height, and so that creates inherent errors and limitations in the climate forecasts or the climate projections. Seasonal models tend to be a little bit better. They tend to be around that 60-kilometre range, and it's also true for global reanalyses for weather over the last 100 years. So the topography in blue looks a bit better, but it's clearly missing a lot of structure. If we go to the sorts of resolutions that are in the current state-of-the-art weather models or the Bureau of Meteorology's regional reanalysis around 12 kilometres, you start capturing a significant amount of that topography, but clearly still missing a significant amount of detail. Even the regional models, the 1.5 kilometre models, are showing a lot better reproduction of that structure, but you can still clearly see that there's the black fine structures exceeding. This has implications for localized information, means that weather systems aren't always well resolved, topographic influences are underestimated, and that has obvious implications for things like microclimates and ecosystems. And if we just zoom in a little bit, we can see that in a little bit more detail some of that missing structure that's in the models. And this data was courtesy of the Bureau of Meteorology. The last thing I want to mention around these weaknesses is understanding what the limitations of the model physics actually are. And so many climate models do not replicate key processes such as ENSO very well. El Nino models can have biases. There's a number of biases that occur in many of, if not all of the leading climate models, and they've been the subject of what we call grand challenges. There's been decadal global efforts to try and improve these models. As an example, the models systematically underestimate the duration of drought. That obviously has significant implications for water, fire, ecosystems, and how we assess the risk of change. Before I close, I want to mention just a couple of things. So one is just we're dealing with this information of flood. That means you need sophisticated post-processing of the data to extract the information that you need to help provide the interpretation, both for automatic and for human interpretation. And then these models are often linked or feed into hydrological models, fire behaviour and so forth. But the real opportunity is the integration and interpretation with combining this with the kind of land use, ecology, hydrological, demographic information. That's going to require the right tools, which in some cases include machine learning and artificial intelligence, but not just. You need to think about what are the questions that you're asking and select the right tools. So I just want to finish with a couple of challenges and messages. I believe that there's an enormous opportunity to build resilience and improve decision making, but you have to understand what your data is, how good it is, what are its limitations. Everybody already is or soon will be drinking from a fire hydrant of data. So integration and the right analysis tools and co-design is absolutely crucial. And so everybody needs to be prepared to use a variety of tools. In this instance, not just projections and forecasts, but scenario planning. And we saw an example of that at the recent workshop at the Royal Society of Victoria, where Lynette Bettiot was talking about what a potential heat wave would look like. And finally, while I've been talking about the physical sciences, we're also, for impact, we're talking about making decision-making under uncertainty. And we need to heed the lessons from statistics and psychologies. And further, in the social sciences, we need to develop common languages internally across the organisation, because there's such a disparate field, but huge opportunities, and externally to get the right messages, to get the smart decisions. So the social sciences have a crucial role going forward. Thank you.